Hey there, you ever see a headline, about some new study and just wonder, can I actually trust this? Well, that feeling, it pretty much comes down to one single thing, the study's blueprint. So today, we're going to pull back the curtain on what's called research design. It's the hidden architecture, really, that decides if what we're reading is rock solid or built on sand. Ready? Let's dive. I mean, it's a huge question, isn't it? We are just flooded with information all the time. Studies telling us what to eat, how to work out, even how to think. So, how do researchers build a study in a way that the answers they get are real and not just some random fluke? That is the exact problem a research design is meant to solve. And this quote right here, it gives us the perfect way to think about it. A research design isn't just some vague idea, it is a blueprint. It's a detailed architectural drawing that a scientist has to create before they can even think about laying the first brick of their investigation. Right, and just like an architect, a researcher can't just show up and start building. Nope. They need that detailed plan, that blueprint, that outlines what the final structure is going to look like. This thing dictates every single step, from how you collect the data to how you measure it and analyze it. It's all about that initial plan. Okay, so let's look at this definition from Kurlinger, because it's actually perfect. He says a research design is the plan, structure, and strategy. And I love those three words. Think about it. The plan is the big picture, the overall scheme. The structure is like the skeleton of the study. What are the variables and how do they connect? And then you've got the strategy. That's the real nitty-gritty. How are we actually going to collect and analyze the data to get our answers? Plan, structure, strategy. Those are the three pillars of a good blueprint. So, what's the number one job of this blueprint? Well, it's to manage something called variance. Honestly, the best way to think about it is like tuning an old radio. Your goal is to find that one crystal clear signal and tune out all the static and noise that's trying to drown it out. And variance is really just a fancy word for the spread or the differences in a set of scores. So let's say you're testing a new teaching method. The variance is simply the difference in test scores between all the students. A researcher's entire job is to figure out what's causing those differences. And this slide just illustrates that perfectly. It's a balancing act. The researcher wants to crank up the volume on the signal, that's the real effect they're studying, while doing everything they can to turn down the volume on two different kinds of noise that can totally mess everything up. Let's break each of these down. First up, we've got the signal. Researchers call this systematic variance. This is the good stuff. It's the variation that you want to find. It's the change in your results that is directly caused by the thing you're testing. A great research design makes this signal as loud and clear as it can possibly be. Then you have what we'll call the outside noise, or extraneous variance. These are unwanted variables that can sneak into your study and totally contaminate your results. For example, say you're testing a new medication, but you don't control for what your participants are eating. Well, their diet could create a lot of noise and make your findings totally unreliable. The goal here is to get that noise under control. And finally, there's the random static, or error variance. This is the background hum that's kind of unavoidable. Little measurement errors, a participant having a bad day, slight differences in the room temperature. You can never get rid of it completely, but a solid blueprint is designed from the ground up to minimize this static as much as humanly possible. Okay, so if the big goal is to control all this pesky noise, how do researchers actually do it? Well, they've got this awesome toolkit of techniques, and each one is basically a different way to build a more stable, noise-proof structure for their study. And there are four main tools in this kit. You've got randomization, which is the big one we'll talk about in a sec, but researchers can also use elimination, which is pretty straightforward. You just remove a variable entirely. Then there's matching, where you make sure your groups are equal on a certain factor. And finally, statistical control, which is where you use some fancy math to adjust for differences after you've already collected the data. But really, the gold standard, the most powerful tool in the whole kit is randomization. It's so cool. It just means every single participant has an equal chance of being put into any of the groups. By doing that, you're making sure that, on average, the groups are pretty much equal on all possible outside variables, even ones you haven't thought of. It's just a beautiful way to control for noise you don't even know exists. And hey, the other tools are super useful too. If you think the gender of the participants might mess with your results, you could use elimination and just study women. Or you could use matching and make sure you have the exact same number of men and women in each group. They're all just different ways to build that solid foundation. All right, so now that we know what goes into making one of these research blueprints, how can we, you and me, as people who read the news, how can we tell a good blueprint from a kind of flimsy one? It turns out there are a few key things you can look for. It really boils down to these three things. Number one, does the study actually answer the question it's supposed to? Number two, does it do a good job of controlling for all those extra variables we've been talking about? And number three, can you actually take the results and apply them to the real world?
So this first one is all about alignment. It's so basic, but so important. If a researcher says they want to study a new therapy, but their actual design measures something that's only kind of related to it, well, the blueprint is flawed from the get-go. The plan has to match the problem, period. Second, it absolutely positively has to control that outside noise. This is what scientists call internal validity. Because if the design fails to control for those other factors, you just can't be sure that the signal you're seeing is real. It might just be an illusion created by all that noise.
And finally, there's this idea of external validity, or generalizability. Look, a study might find some amazing result in a super controlled lab with a very specific group of college students. But if those findings don't apply to a bigger population out in the messy real world, its usefulness is, well, it's pretty limited.
Okay, theory's great, but let's make this all a little more concrete. Let's take a look at a simple but really powerful blueprint that puts all of these ideas into practice to build knowledge that we can actually trust.
This one is a total classic. It's the pre-test, post-test control group design. Just look at how elegant this structure is. You start with two groups, and you create them through random assignment. That's what the little R means. Both groups take pre-test. Then, and this is key, the experimental group gets the treatment. That's the X, while the control group gets nothing. Afterwards, they both take a post-test. See what this does? By comparing the change in scores for both groups, you can isolate the true effect of the treatment. It's such a great design for controlling noise. And that really brings us right back to the main point of all of this. It doesn't matter how fancy the statistics are, it doesn't matter how exciting the conclusion sounds. If that initial blueprint, the research design, is weak, then the whole structure of knowledge that's built on top of it is just unstable. The foundation is absolutely everything. So I'll just leave you with this question to think about. The next time you see a headline about some groundbreaking discovery, just pause for a second. Before you buy into the conclusion, what's the first thing you're going to ask about its blueprint? Was there a control group? Did they use randomization? Because now you actually know how to look behind the curtain and judge that foundation for yourself.